Yeah, so today with us, we have two speakers from the NetMod Lab at the National Technical University of Athens. So specifically, it's Dimitrios and Nikos. And Dimitrios specifically is a postdoc fellow at the NetMod Lab, and he's basically focusing on IoT and cyber-physical systems and how edge and cloud computing plays a role here. And maybe you even know him from different EU projects that has happened over the years, and they are still happening. So he's very active in the research community around the IoT systems. On the other hand, Nikos is a PhD. He's pursuing his PhD at the same university, and he's basically working on more intelligent orchestration mechanisms for cloud on edge, and also different techniques like reinforcement learning and also software stacks for IoT. And today, basically, they will be talking about the Nefele project and more specifically the open source stack that they have developed there, and how this open source software stack enables IoT virtualization and how it can be used for convergence with the edge computing technologies. So with this, Dimitrios, you can take the screen.
Thanks for the invitation and for giving us the opportunity to present what we are doing in Nefele. I'm Dimitrios Patharakis, and along with Nikos, we are going to present you today the open source software stack that we have developed during the Nefele project to solve mainly virtualization and convergence challenges of IoT with edge computing technologies. So Nefele project actually will be finalized in September. The purpose of the project was to provide a lightweight software stack and the synergetic meta orchestration framework for the next generation compute continuum. So we try to integrate the IoT part with the rest of the cloud continuum infrastructure. So a few words about our lab here in National Technical University of Athens. So we come from the Network Management and Optimal Design Laboratory called NetMod, which is under the School of Electrical and Computer Engineering of NTUA. So NetMod has 5 professors, many postdoc researchers, more than 20 PhD candidates. And the main focus of the lab regards the 5G, 6G communication and computing systems like edge, fog, or cloud computing, the optimal resource allocation and orchestration, data modeling, dynamical systems modeling and optimal decision making, hardware, software co-design, and so on. Our lab is actively involved in various EU and national projects, and you can find also the link of the laboratory here. So when we started the Nefele project, actually we identified 2 main challenges, and also working together with Eclipse, the need for convergence of various IoT technologies, trying to guarantee seamless and continuous openness and interoperability, and try to build a solution that could provide the backbone as a software for all the use cases that we had in the project. And more than that, we tried a main challenge was to provision an integrated meta orchestration environment, or as we call it, platform, for the hyper-distributed applications orchestration, trying to build a synergy between IoT, edge, and cloud platforms. So the general vision of our project was to build a systems, relying on a system of systems approach, beginning from a meta orchestration and going to different levels of control regarding the cloud computing infrastructure, the edge computing infrastructure, and the IoT devices, to build several orchestration mechanisms that work together, trying to provide convergence with IoT, with the IoT part and the edge cloud. And the main scope was to provide to develop and provide the software stack and achieve interoperability across the whole continuum to facilitate the orchestration and deployment of distributed applications. So this is a very short overview of what we are doing in the project. Just here, we just want to mention that in the beginning of the project, what we did was to find an old implementation of Web of Things in Python. So what we did in the first place was to update the repository of the old Python implementation, update all the packages, and provide some extensions in the software necessary for the means and what we try to do in the project. And actually, we, upon the extension of WhatPy 2, as we call it, we provide a software stack that acts actually as a wrapper, binding the WhatPy implementation with additional functionalities to enable the orchestration of IoT application graphs. And therefore, we have also two implementations of the VO-WHAT, both the one is interoperable with W3C Web of Things, and the other one is interoperable with Open Mobile Alliance and lightweight machine-to-machine semantic. Just for the presentation, we have here two definitions that we utilize throughout our work. The first one is the definition of the virtual object, as we call it, VO, which is the virtual counterpart of a physical device on the Internet of Things domain. So the VO provides a set of abstractions for managing any type of IoT device through a virtualized instance that is usually deployed in the edge of the network, trying to augment the supported functionalities of the devices through this software stack that we call it VO stack. The second definition is the composite virtual object, which is a software entity that is able to manage different virtual objects. So it is like an aggregation point for data coming from multiple VOs to provide also advanced functionalities and be part usually of an application graph. So this applies both for the VOs and CVOs that we consider that is the entry point for data coming from the IoT layer towards application graphs that we deploy across the continuum. Just to mention that the VO stack implementation is part of the W3C Web of Things developer resources, and we try to build an active community, both coming from the use cases of Nefele project and also during the support of the two open call phases that we had in the project. So we had a lot of developers that tried to utilize our software to provide application graphs that consist of VOs and CVOs. So here I will go into a bit of details about what we are doing, the extensions that we have in the Python implementation of Web of Things and the VO stack. So we will start with some general assumptions that we had, or let's say directions that we have regarding the VOs. And specifically, we consider that the VOs are deployed on edge servers and consumes things. And here we will refer to this presentation to the Web of Things implementation. So we have two deployment types. We consider that we may have some devices with computing capabilities, or either we can have some devices without computing capabilities. So for the second case, for example, some sensors are able to perform read-write operations directly, accessing the URLs of the exposed thing as part of the Web of Things standard. In the first case, we consider that the virtual object contains both a consumed thing and an exposed thing. The exposed thing is utilized as a northbound interface towards CVOs or application graphs, while the consumed thing is able to interact with an exposed thing that runs on a device with computing capabilities. So these are the two deployment types that we utilize throughout the project. Just to give you an example here, this is one of the use cases of the project. So you can see that we have several application graph nodes that have some application components or VOs and CVOs. And here we define, let's say, a business logic, taking data coming from the device layer that are redirected towards the virtual objects through some gateways, utilizing here the MQTT protocol, and trying to have different communication schemes and support advanced functionalities using the composite virtual objects to facilitate the specific application graph. This is just an example of what we are trying to build. So here we have the virtual object stack architecture. So we have three main layers. The first one has to do with the physical convergence layer. So we consider that we can support several devices and more specifically, several communication protocols, HTTP, MQTT, CoAP, WebSockets, and Xeno, and I will go through the details afterwards, and different security schemes, trying to solve the convergence challenges between the digital replica, so the virtual object, and the IoT devices that are part of, for example, the physical layer. The second layer has to do with the backend logic layer, which actually implements some functionalities that the virtual object wants to augment to the IoT devices. So, for example, we have developed two databases, one for time series data and one for more static information coming from the devices. And we have a set of functions that we will speak in the next slides, trying to provide intelligent mechanisms to the devices. For example, we can have custom logic about the Web of Things events and actions, or provide task offloading modules or TinyML implementations trying to achieve different levels of control, both for the device part and the application graph. So for the third layer, the Edge Cloud Convergence layer, we are exposing a lot of information towards the synergetic meta orchestrator that we developed in the project. So we want to solve scaling issues regarding the virtual object, for example, or to provide the necessary monitoring, expose the properties or the metrics towards a monitoring system, and try to solve multi-tenancy issues and challenges. So this is the architecture of the VO stack. And one important note is that because we are using virtualization to develop virtualization solutions to deploy the VOs, we bind all this information utilizing a common descriptor that we call it VO descriptor, used both for the virtual objects and the composite virtual objects. So we consider that we can deploy the VOs, for example, in Kubernetes or Docker environments, and provide, along with the VOs, some sidecars and extend the functionalities with, for example, ML-based network agents or ML-based orchestration agents. But we have a couple of slides with works that we have done the last year about these examples. So what is quite important is that when we started the project, we were trying to find out a way to facilitate the development of virtual objects to developers or people that don't have a lot of experience with the Web of Things. So we came up with an idea of actually trying to automate the process of the instantiation of virtual objects. So this means that we have developed a a CLI, as we call it, or a script runner, as you can see here in the figure, that takes 3 different files, the thing description of the thing based on the W3C Web of Things standard, the Python script that usually is contained in the examples of Web of Things, and also the virtual object descriptor that we have developed, and Nikos will speak about this later on in his presentation. So these 3 files, actually, we utilize them, we parse these files, and we try to automatically instantiate a virtual object that has a specific thing descriptor, has some custom functionalities coming from the Python script with some conventions that we have, and also taking as a declaration all the things that the VO descriptor contains. So, for example, in the VO descriptor, a developer can state that wants a specific database, and the script runner is able to instantiate a virtual object that also contains, for example, InfluxDB. So here in this slide, we have, let's say, the 4 main extensions that we did in Web of Things, in the Python implementation of Web of Things. We have extended some protocol bindings. We have extended or developed again some security mechanisms. We have included some periodic functions that we are able to repeat some functions in irregular intervals. And we have added InfluxDB and SQLite as databases to store information of a thing. So this means that the supported protocol bindings right now for the Python implementation of Web of Things are HTTP and HTTPS, CoAP, WebSockets, MQTT, and we have included also Zeno protocol, which is a PubSub protocol like MQTT that is based on Zeno routers. It is a quite new protocol developed to facilitate robotic applications. So we needed to develop this under the Nefele project. Also, we have developed some authentication mechanisms, basic username password authentication schemes, and better token authentication to facilitate the trusted part between the data exchange of the application graph and the VOs. Also, we have the InfluxDB integration, so we automatically, each time a property has a new value, we use some buckets in InfluxDB to save and store this information and data. And also this facilitates the process of, for example, time series analysis, or at some point we had some predictions as external functions of the stack. So we have a time series database that also logs action invocations or event emissions, and also is able to propagate this information in a centralized monitoring engine as we had in Nefele. InfluxDB is also able to be deployed as a sidecar in case that we have a virtualized environment like Kubernetes. So here we will speak about the VO stack functionalities that we have developed and we continuously develop to support all the research work that we are doing in the lab. So 5 main categories. We have a lot of work trying to provide automatic orchestration and virtualization of the stack. We had some security mechanism, OpenID for verifiable credentials, but I will speak about this later. We have an RTSP server for video streams, some network optimization sidecars, and a proxy mode that I will discuss in a few slides. So one by one, what we did was trying to deploy the virtual object as a Kubernetes deployment. So we started with developing a specific Docker image for the virtual object, and then we developed a Helm package that was quite helpful because we could override the defaults. with developer declared values. So facilitate the whole process of developing custom VOs or VOs that are quite similar to each other. And this also means that we were able to integrate the virtual objects and the composite virtual objects in a microservice-based architecture that we call application graph. So the second part has to do with OpenID for verifiable credentials. So here, what we assumed was that there is an issuer component that actually is able to issue credentials, trying to provide access control to the information, for example, that a VO stores. So here we have an example that a CVO wants to communicate with a virtual object, and the workflow actually is that the VO uses a holder sidecar that stores the specific credentials, and the CVO queries the issuer and then tries to get some information from the virtual object. And actually this the virtual object proxies the request through the holder to verify the credentials of the CVO. So this was quite helpful to realize the trusted data exchange between the application graphs that we had in the project. Also, we have developed an RTSP server as a sidecar. So actually, we have FFmpeg library that redirects a video stream to a specific sidecar. And we have developed a video property that can be exposed as a URL through the video stream. So we are using a redirection to the RTSP server, but the video is stored as a property under the Web of Things implementation. Also, utilizing VOs and CVOs, we were able to proxy different invocations. So, for example, for read-write operations, or to proxy some action invocations, subscriptions, and proxy also events. We were able to declare, utilizing the VO descriptor, this mode that, for example, a VO that needs to proxy a specific event towards an IoT device. So we consider that we have an event that is emitted for some reason in the layer of the virtual object, but then it needs to communicate with the IoT device to control it or change some parts. We were able to proxy this event to another exposed thing. Here we have also two examples that we developed during the project that has to do with software-defined networking. So we had some topologies in the IoT level, and the virtual object acted as a controller for reactive routing in the first case, and in the second case of time-sensitive networking, the virtual object communicated with the dedicated netconf server deployed in an IoT gateway in the physical layer, providing different schedules for the TSN. This is just two examples on how to control, for example, different network capabilities utilizing the virtual objects. And more specifically, we have developed some digital twins, and we believe that this modular nature of VOs and CVOs that work together is able to provide the modular DTs to actually control, from the one hand, the physical layer that consists of IoT devices, access network, or different communication protocols, and from the other side, the application layer. So we can have different application requirements, many application graphs, and for example, one of the main challenges is to provide adaptive orchestration and resource management. So the VO acts here as a bridge between these two layers, trying to control, from the one hand, the the devices, and from the other hand, to expose information that can be capitalized and used from an orchestrator for the application layer. So we have here two different examples. The first one was a research work that we submitted recently, that the virtual object in the first level has a specific reinforcement learning agent that takes information about the quality of the transmission coming from a device and controls the rate that the device sends information towards an application graph. And this information is pre-processed in the virtual object and propagated to a CBO and then to specific pods that has a specific business logic. Here, the image was first, it goes through, each offloaded image goes through a noise reduction application and an image detection. So this was to an inference application graph. So the composite virtual object here also provided to the dedicated Kubernetes infrastructure that we had, utilizing a simple machine learning algorithm, provided the scaling decisions for the application pods, considering also historical data and previous decisions. So the second example that we also submitted research work recently was in the context of Internet of Robotic Things. So here we consider that we have a robotic agent that has the capability of performing some object detection and inference application on premises, or to offload to a more powerful edge server that has also the capability, for example, to deploy LLM services and provide more information about the inferred image. So here we just showcase again how we utilize the virtual object that we deployed as a sidecar, an AI-assisted mechanism that controls the task of loading in this scenario. And also the virtual object was able to emit an event and trigger the automatic or on-demand deployment of resources, exposing a specific metric in Prometheus, and providing this information to the synergetic meta orchestrator layer to deploy the applications on the edge server on demand. Coming to the end, we have a roadmap for the next period for this software. We want to keep it alive, and more specifically, we are going to follow the ongoing activities for W3C Web of Things, try to see that now that we have a bit more time, try to see what updates there are in the specification or in Node.js implementation, and try to see where we can contribute also in the Python implementation. So what we aim to do is to support and develop new features in WhatPy in the Web of Things Python implementation. Also, we aim to release the VO stack either as an Eclipse open source project or as part of Eclipse Things Web. And here we would like also to thank Eclipse for the fruitful collaboration that we had all these years and the support they provided. Finally, we are going to continuously work and provide contributions to the VO stack to bridge the gap between orchestration and control of IoT devices. Here you can find the links towards the GitLab repository hosted by Eclipse, and also the documentation that we have developed for the VO stack. And I think that's it. Just a final thank you to the Web of Things community for the continuous interaction and support all these years.
Hello everyone from my side as well. My name is Nikos. So I will show you briefly the documentation that we have created for the VO. So for example, I think the important part here is the YAML file that has the video descriptor that we talked about before, that Dimitris talked about. And it basically avoids having all the boilerplate code of instantiating HTTP servers, MQTT servers, which ports they will use, etc. So all the configuration options will go in here. And once we start the script runner, this file will be read and the VO will be automatically configured. So yeah, we have more info here if you want to have a look. And right now, the code, as we showed in the last slide of the presentation, is hosted at Eclipse Research Labs, which you can see over here. So yeah, we have also prepared a video. So yeah, specifically this one will show an example of using the Influx DB database, which we use to automatically save all property values, to log all action invocations, and all events that have been emitted. So over here we have the coffee machine example. Right now I started the VO and I use the client to consume its data. And over here we can see, for example, that we can find historical data about the property values, which are stored here. And later on, users can work with this data and extract more useful info. So moving on, over here, I would like to highlight how we do the mapping between the various properties, actions, and events, and the Python code. So for example, here, by using specific names for the properties, the values, and the events, we can bind them to specific parts of the code. So over here, we have the all available resources property. And by using a variable with the underscore init name, we can basically feed the initial value of the property. The same goes for the next few variables. Yeah, then we have a property that can be observed, and over here we have all the functions that will run once certain events have been emitted. We can also specify specific write handlers each time we write to this property. Over here we have a handler for an action that is to make a drink, and it contains all the logic about this action. And lastly, we have a set schedule action that again is bound to this code. So lastly, we have the Nepheli platform, which includes a platform where we can store specific artifacts. So over here we have VOs, CVOs, and we can also host application components saved as Helm charts. And we connect all of these by having application graphs. So we have created a YAML file that includes all the software components. Over here we can see visualization of the graph as well. And assuming, of course, that we have a Kubernetes cluster deployed somewhere, we can also request the instantiation of this graph. And after we click Save and Start, our application graph will be sent to our synergetic meta orchestrator component, which will then deploy the graph. So yeah, over here we can see that the graph has been deployed. Sorry, but I kept that a bit too short. Yeah, and that's all from my side.